Hello friends, continuing with the topic of electric potential, we come to the second stage where we try to understand about the electric potential itself. So how we try to understand at the second stage? Let us see electric potential at a point in an electric field. We have to define it. So let us define electric potential at a point in an electric field. I define the work done in bringing a unit positive charge, that is a test charge, from infinity to the point in an electric field against repulsive forces is defined as electric potential at a point in an electric field. I repeat, the work done in bringing a unit positive charge, that is a test charge, from infinity to the point in an electric field against repulsive forces is defined as electric potential at a point in an electric field. It is denoted by V or phi. Now look at the diagram. Here is the field region, the limits of the field, and it's a test charge Q naught which is brought to point P in the electric field of plus Q. Okay, and the work done in bringing Q naught from infinity to point P against repulsive forces is defined as electric potential at a point P in the electric field. Mathematical expression. If W be the work done in bringing a unit positive charge Q naught from infinity to the point P in the field of the charge plus Q against repulsive forces, then electric potential at P, say V, is equal to limit Q naught approaches 0 W by Q naught. So V is equal to W by Q naught, where limit Q naught approaches 0. Why Q naught should approach 0? Because if Q naught is having a larger magnitude, then it will have its own electric field and will deform the results. Okay, so it must be very small, that nearing 0. Now SI unit, since we know V is equal to W by Q naught, limit Q naught approaches 0. Now SI unit, since we know V is equal to W by Q naught, limit Q naught approaches 0. Therefore for W we write J, joule, J, and for Q we write C, charge, C. So joule divided by coulomb. So it becomes joule per coulomb or volt. Now definition of volt. Since we know electric potential at any point in an electric field is given by the expression V is equal to W by Q naught, limit Q naught approaches 0. Now when W is 1 joule, Q naught is 1 coulomb, then W can be expressed as equal to 1 joule divided by 1 coulomb, or it is equal to 1 joule per coulomb or 1 volt. Thus electric potential at any point in an electric field is defined. Thus electric potential at any point at a point in an electric field is said to be 1 volt when 1 joule of work is done in bringing 1 coulomb of positive charge from infinity to the point in the electric field. I repeat, thus electric potential at a point in an electric field is said to be 1 volt when 1 joule of work is done in bringing 1 coulomb of positive charge from infinity to the point in the electric field. A type of quantity, it is scalar quantity. Okay, electric potential is a scalar quantity. Now, significance of studying electric potential. Electric field at a point in an electric field is a vector quantity, and it is difficult to deal with vector quantities, whereas electric potential at the same point is a scalar quantity, and it is easier to deal with scalar quantities. It is therefore study of electric potential at a point in an electric field is preferred over electric field at the same point in the electric field. I repeat, it is therefore study of electric potential at a point in an electric field is preferred over study of electric field at the same point in the electric field. So this is how important is study of electric potential at a point in an electric field being scalar quantity. Now, electric potential due to a point electric charge at a distance r from it. Physical situation. Consider a point electric charge plus q lying in any region of space. Let P be any point at a distance r from it where electric potential is to be determined. Now, work done. Let there be any charge q naught brought from infinity to P against repulsive forces. Then work done, say W is equal to K naught Q naught by R. Okay, I repeat, let there be any charge q naught brought from infinity to P against repulsive forces. Then work done, say W will be equal to K naught Q naught divided by R. Now, third, electric potential. Because electric potential V is equal to W by Q naught, or it is equal to K naught Q by R. Because Q naught W by Q naught shifts to the right hand side under W, so it will become W by Q naught, and W by Q naught is V, electric potential V. VR, R means R within bracket shows that it is V at a distance R from the charge plus Q. So therefore we can write VR is equal to K naught Q by R. Okay, so the electric potential due to an electric charge at a distance r from it is given by the expression V is equal to K naught Q by R. If the charge is negative, then it will be V is equal to minus K naught Q by R. Okay. Now, discussion. First point, V depends directly upon magnitude of charge. The formula, if we look at the formula, we see that V depends directly upon magnitude of the charge. Number 2, V depends inversely upon distance of the point from the charge. Number 3, also V depends upon the medium between the point and the charge, as VAR is equal to KA Q by R. R we can write it as V naught by epsilon R, because K naught is equal to 1 by 4 pi epsilon naught, and 1 by 4 epsilon naught Q by R is V naught. Okay, therefore we can write VA within bracket R equal to V naught divided by epsilon R. It means electric potential reduces in the medium by a factor equal to relative permittivity of the medium, the dielectric constant of the medium. Now assignment 2.1 continued. Question number 4. What must be the magnitude of an isolated positive point charge for an electric potential of 100 volt at a distance of 10 centimeter from the charge? Okay, just to substitute the values and then find out the result. Now relationship between E and V, that is electric field and electric potential. Physical situation. Consider a point electric charge plus Q lying in any region of space. Let P be any point in its field at a distance R from it. Okay, this is the situation. Now let us find electric field at P as well as electric potential at P. First we find electric field intensity at P, say E, and it is equal to K naught Q by R square directed away from the charge. Let us mark it as equation 1. And electric potential at P, say V, is equal to K naught Q by R. Let us mark it as equation 2. And now relationship. Next slide please. Now relationship. Dividing equation 2 by 1, we get V by E is equal to K naught Q by R divided by K naught Q by R square, and it is equal to R. Or we can write E is equal to V by R, or we can write V is equal to E into R. This is how the relationship exists between E and V. Either you write E is equal to V by R, or you write V is equal to E into R. Now, if we plot graph, then E versus R graph is shown by red and V versus R graph is shown by green. So there is a difference of slope between the two graphs. Okay. Now another SI unit for electric field. Since E is equal to V by R, therefore for V we have volts and for R we have meters. So therefore electric field intensity assumes a new SI unit, V divided by M, or V M inverse, that is volt per meter. So volt per meter is the new SI unit for electric field, whereas the previously we have learned that electric field intensity has a unit newtons per coulomb. So both the units you remember, both are for electric field intensity. Okay, so you may be you may not get confused in numerical problems. Sometimes they write Newton per coulomb, sometimes they write volt per meter. Okay. Now assignment 2.1 continued. Question number 5. Electric field intensity at a point in an electric field is 20 Newton per coulomb, and electric potential at the same point is 10 joules per coulomb. Calculate magnitude of charge and distance of the point from the charge. Okay, find out. Question number 6. Name the physical quantities which has the following as their SI units. Number 1, Newton per coulomb. Number 2, volt per meter. Number 3, Newton per coulomb meter square. Number 4, voltmeter. So next part we are to study about electric potential at a point due to number of charges. If number of charges are given, then what will be the electric potential at a given point? Now consider n charges Q1, Q2, Q minus Q3, Qi and Qn as shown in diagram. Let P be any point at a distance R1, R2, R3, Ri and Rn respectively from the charges. If V1, V2, V3, Vi, Vn be the electric potentials at P respectively, then total electric potential at P would be, say, V equal to V1 plus V2 plus V3 plus so on Vi plus so on Vn. Okay, so it is algebraic sum. You can add up because electric potential is a scalar quantity. It's easier to deal with electric potential. Now V will be equal to, substituting the values of V1, V2, V3, Vn etc. we get V is equal to K0 Q1 by R1 plus K0 Q2 by R2 plus K0 minus Q3 by R3 plus so on K0 Qi by Ri plus so on K0 Qn by Rn. So this would be the total electric potential at P. It is algebraic sum, so you need not worry about the signs. So whatever signs has been allotted to the charge, you put the same sign. Assignment 2.1 continued. Question number 7. What is the electric potential at the center of the sphere as shown? Given Q1 equal to 10 raised to power minus 8 coulomb, Q2 is equal to minus 2 into 10 raised to power minus 8 coulomb, Q3 is equal to 3 into 10 raised to power minus 8 coulomb, Q4 is equal to 2 into 10 raised to power minus 8 coulomb. And the answer would be 360 root 2 by A volts. Question number 8. 2-point electric charges 4 microcoulomb and minus 2 microcoulomb are separated by a distance of 1 meter in air. At what point on the line joining the two charges is the electric potential 0? Calculate. The question number 9. What is the electric potential at the surface of a solid nucleus with atomic number 79 and radius 6.6 into 10 raised to power minus 15 meter? Question number 10. Is electric potential necessarily be 0 at a point where electric field intensity is 0? You give the answer to this question. Now let us understand electrical potential energy of a charge in an external electric field. So since we know electric potential at any point in an electric field is given by the expression V is equal to W by Q naught, where Q naught approaches 0. Therefore, work done in bringing any charge Q naught in an electric field is, say, W is equal to Q naught into VR, or it is equal to Q naught into ER, because V is equal to E into R, where VR is the electric potential at the point whose position vector is R, as shown in diagram. This is the point P, this is the point P, this is distance R from origin. Okay. Assignment 2.1 continued. Question number 11. A part, deduce the expression for the potential energy of a system of two charges Q1 and Q2 located at a distance R1 and R2 from origin respectively in an external electric field. Assignment 2.1 continued. Question number 11. A part, deduce the expression for the potential energy of a system of two charges Q1 and Q2 located at a distance R1 and R2 from origin respectively when placed in an external electric field. B part, 3-point charges plus Q, plus 2Q and minus 3Q are placed at vertices of an equilateral triangle ABC of side A. If these charges are displaced to the midpoints ABC, A1, B1, C1, if these charges are displaced to the midpoints A1, B1, C1, A1, B1, C1, if these charges are displaced to the midpoints A1, B1, C1 respectively, find the amount of work done in shifting the charges to the new locations. Okay. So this is all about electric potential at a point in an electric field. Thank you so much. God bless you. Next time we'll take up electric potential due to an electric dipole at a distance r from its midpoint. Okay. Till then, goodbye.